Hello. My name is Ingi Hong, and this is um peer teaching assignment for computer science course for 42, and my topic is retriever augmented generation. So before I'm talking about RAG model, I'm gonna first talk about LLMs, large language model, which is we should first know about it. So LLMs are advanced deep learning system trained on extensive data to understand and generate human-like language. They utilize transformer neural network architectures, which processes entire sequences of text in parallel, enabling efficient training and the handling of vast amount of data. In LLM, there are key characteristics. First one is transformer architecture. This is architecture that build LLMs, which compromise with encoders and decoders with self-attention mechanisms. This allows the models to grasp the context and relationships between words and phrases effectively. Also, it has massive scale. These usually contain hundreds of billions of parameters, so it helps enabling them to process and learn from massive dataset like Common Core and Wikipedia. So when they is also related to ethics, but basically when they are training their LLMs, they usually web crawling, so they get data from online where they can access, and these are how we make data set for training LLMs. So this is representation of how large is for LLMs. So in 2018, BERT large had 345 billion parameters, and in 2019, GPT-2 has 1.5 billion, and 2020 we have GPT-3, which has 175 billion parameters, and in 2021, Turing Megatron Energy model has 530 billions. In 2023, we estimate that GPT-4 has 1.4 trillion parameters. So in the left side of the figure, it's showing the neural network layers. We first have input layers, and it passes through hidden layers, and it goes to the output layer, and the number of the layers and parameters are the right side. And we see that as time goes on, the number of parameters are increasing, and we see that the performance of LLMs are, for now, linearly increasing as they increase the number of parameters. So we see that in here, we can assume that for now, like a Moore's law, it applies, the same stuff is also applying for in LLM world. So first, we're gonna talk about the transformer architecture. The right side is for your understanding. I prepared the figure of the encoder and decoder, which comprise transformer architecture. So transformer architecture is introduced in the 2017 paper. Attention is all you need. So it is neural network design that has revolutionized natural language processing by effectively handling sequential data without relying on recurrent structure. So key components of the transformer architecture is first encoder, decoder structure. So encoder, as we seen here, process input data to generate contextualized representations, and decoder utilize these representations to produce the desired output, such as translated text. So decoders here. And the attention mechanism allows the model to weigh the importance of different input elements when generating each part of the output, enabling it to focus on relevant information. So when we have this layer, these are the weight in here, and this adjusts the importance and makes the architecture know which one is more important. And third one is multi-head attention. It executes multiple attention operations in parallel, capturing various aspects of relationships between input elements. In position-wise, feed-forward network applies fully connected layers to each position separately, enhancing the model's capacity to learn complex transformations. So we also have positional encoding, which incorporates information about the positions of tokens in the sequence, compensating for the lack of inherent order processing in the architecture. So here's the transform architecture. So when we train LLMs undergo self-supervised or unsupervised learning, where they predict missing part of text, enabling them to learn grammar, facts, or maybe some reasoning if they have so many training undergoing. So in here, we don't explicitly label the data. So, and they just learn by figuring out how. And this process involves significant computational resources and large data sets to capture the nuance of human language. So this is the reason why nowadays the NVIDIA is skyrocketing for their stock because it's first invented for graphic for taking over the graphic works instead of CPU. So it's more specified version of CPU. But now we figure out that working graphic is also similar with working for training. So they now use graphic card for more training their LLM models. And the LLMs work by first pre-training. The model is trained on massive data set like book, articles, or website. And it uses self-supervised learning where it predicts missing word in sentence, as I've said before, and it develops an understanding of grammar, fact reasoning, and patterns of it. And we also have fine-tuning, which a pre-trained model is adjusted for a specific application, like chatbot translation, coding, or etc. So supervised learning or reinforcement learning is used to refine responses. So it first have pre-trained model and we use some specific domain data set to train again so that our LLM models are more fit into some specific operation or some purpose or for some industry. So we have the application of LLMs. First, we have natural language processing task, NLP task. So it first generates some text like writing essay, reports, or stories, and some creative content. Also, it has like machine translation, so we can now have automatic translation between language. Also, we can work on summarization, which condensing long documents into concise summaries. Also, we have sentiment analysis, which detecting emotions and options in the text. Also, we have conversational AI, which is like OpenAI or Bard. We are saying like chatbot and virtual assistants. So it helps for customer support automation. Or we also can use for some code generation. Nowadays we have like Copilot in GitHub or maybe CodeLlama. These are incorporated with IDE. So when when we do some coding, they suggest some code or detect some error and suggest for correction. Also, we can use for medical and scientific research. They assist in drug discovery and medical diagnosis. Recently, also we processing large-scale scientific literature. The recent Nobel Prize, the recent Nobel Prize are awarded to some computer scientists because they made some AI which can predict, I guess, like protein structure. So now LLMs and these AIs are using in various fields, even in science. Also, we can use it for legal and business use cases. So we can have contract analysis and document processing and automate email and report generation. Also, we can use some requirement engineering. So when we have contract, we can generate some contract and continuously get some support from the AI agent where we can have more contract like this. We also have like challenges and limitation. First one is bias and ethical concerns. Because of our data set can be biased in some aspect, when we train those data, then our LLMs can get bit biased. And we also have like ethical concern how we get the information from, or how the outputs are representing some maybe idea or like ideology. Those ethical concerns still remaining. Also, we have high computational cost. So training requires massive GPUs and TPUs. And nowadays, not only we need so many computation in occurring in GPU, TPU, in order to do that, we need more electricity, more money for GPUs like this. So their cost for inventing new LLMs are getting too much high. We also cannot avoid hallucination, which generate false or misleading information. This is the main concern for a user. And nowadays, LLM users are keeping in mind for the hallucination and still they have to check whether their information from AI is still correct or not. So they have to double check for this. Also, it has some data privacy risks. So when we input our some sensitive information like our maybe personal information, then it gives some output, but maybe that data also can be stored in somewhere else. So we have that kind of risk for that. Unfortunately, due to the nature of the LLM technology and its drawback, responses generated by LLMs are unpredictable. Additionally, LLM training data is static, which makes hard to update LLM with recent data set. When they have new data, then they have to undergo again for the huge training processes, which takes too much computational cost. So it's kind of redundant. So LLMs are remaining static. So here's the new model using LLMs. This is retriever augmented generation. This is the technique that enhances the capabilities of LLMs by integrating external data source into their response generation process. This approach allows LLMs to access up-to-date and domain-specific information without the need for retraining, resulting in more accurate and contextually relevant outputs. So we have some benefits for RAG. The first one is cost effectiveness. By leveraging external data without retraining, organizations can enhance LLM performance and minimize computational and financial costs. Also, it improves the accuracy. Access to authoritative and up-to-date information. So here means maybe accurate and right information, which is very recent. We can reduce the likelihood of LLMs producing outdated or incorrect responses, and we can also avoid some hallucination in this case. Also, it is domain adaptability, which enables to tailor the outputs to specific domains or organizational knowledge bases, enhancing the relevance of responses in specialized contexts. And in the perspective of RAG cost, since embedding models are now relatively inexpensive, the primary cost of RAG systems stems from vector database hosting and LLM inference. The most significant cost factor in LLM inference without RAG system is typically the number of semantic search results included in the prompt. While incorporating more search results may enhance response quality, it also increases token consumption and potentially lead to higher response latency. Adding more information to a prompt does not always guarantee a better response. The ideal number of results to include varies by system and depends on factors such as chunk size, information density, redundancy in the data, the breadth of user queries, and more. And this is RAG system architecture. The first one is the search layer, and second one is generative layers. So these whole things are RAG system. To explain just briefly from here, is get document, web, and information, the recent one, and this goes in embeddings, vectorized embeddings, and goes to VectorDB. And then when we get input by the user, then it goes to the vector DB here, which is here, and find the most relevant information, and it's added to the prompt, which goes to the LLMs. And then it gets answers from there. I will gonna explain more in detail from now. So as I mentioned before, there are two key components of the RAG system. The first one is semantic search layer. This is composed of an embedding model and vector store. We also have generation layer, or maybe you can say query layer, which composed of an LLM and its associated prompt. So semantic search layer comprise two key components, which is embedding model and vector store, or we can also say database. So these components enable the semantic search layer to build a knowledge base by gathering documents such as PDFs, Markdown, text file, Word, or more other stuffs. Also, it read and segment these documents into smaller pieces called chunks. So and transform the chunks into embedding vectors and store the vectors in a vector database alongside the original chunk text. So this part. So to explain more detail about embedding model, so embedding models are encoding text. They represent text into a numerical representation in vector, which is the same with original text semantic meaning. So it's here, and it goes. We have the text in here, then it goes to the embedding model, then it is translated in vector, and then embedding vectors that represent the text with similar meaning tend to cluster together with the n-dimensional embedding space. We see here it is n-dimensional embedding space, and since we're translate every word in vector and the similar meaning of the word in the documents are gathered, clustered together in embedding space. So we also have vector store. which were database. So database stores on specialized database. Specialized. So vector stores are specialized database for handling high-dimensional data representations. We say vector. So they have specific indexing structures optimized for the efficient retrieval of vectors. Vector stores can be in memory, on disk, or even fully managed, like Pinecone or VV8. For generation layer, it consists with two things. First one is LLM and second one is prompt. The generation layer takes the user query as input and executes a semantic search to find the most relevant information for the query. And it inserts the most relevant chunk of text into a LLM prompt along with the user query and calls the LLM to generate the response. So this is for here part. Query gets inside here and it goes to DB, then find the relevant data and it's attempted to put into the prompt with user input and goes to the LLM models. As for here, LLMs are transformer architecture, as I explained before, that use the attention mechanism to help the model decide where to pay more or less attention in a sentence. LLMs are a part of RAG system are enabled to generate better answers based on the context retrieved through semantic search. LLMs can change its responses to improve a line. So we also have prompt part in here, generation layer. The prompt is a texture input provided to an LLM that essentially programs it by refining, enhancing, or customizing its capabilities. In RAG systems, the prompt includes the user's query along with pertinent contextual data retrieved from the semantic search layer, enabling the model to generate a more informed response. So as I briefly explained before, I'm gonna explain for now for the step of RAG models how it works. The first one is external data generation. The system collects data from external source like API, database, document repositories, web page, and structured dataset. For here, when you want to make some offline RAG model or your private model, which you want to specialize in some part, then you can prepare your own data sets like your documents or maybe your information, which is organized in some document or repositories. These documents are text-based information transformed into embeddings, which are numerical representation of vector data. And these are in vector form. And the embeddings are stored in a vector database to enable efficient retrieval. Reason why we do vectorized is because vector is consists with in numbers, so it's more easier to achieve and retrieve the data from there. And the second step is relevant information retrieval. When a user submits a query, it is converted into a query vector. The system performs a vector search in the vector database, identifying and retrieving documents that are most relevant to the query. This retrieval process ensures that the model has access to the most relevant knowledge beyond its training data. LLM prompt enhancement is the third step. The retrieved data is appended to the user's original query to enhance the prompt. By incorporating this external knowledge, the LLM receives a contextually enriched input, allowing it to generate more accurate and relevant responses. So when we do some prompt engineering, which I will gonna explain more about later. We know that when we enter the better prompt, then LLM's gonna give us better responses and better answers. So with this, this has the same perspective that in origin model, we are giving the exact information from our own database, which is recent and correct by using our original query. And then that retrieved data is incorporated with our original query and then sent to the LLM. So this enriched prompt makes better output from the LLM. So next step is origin response generation. The enhanced prompt is sent to the foundational model like OpenAI, GPT, Llama 2, and the LLM generates a response that integrates the retrieved external knowledge. This process ensures that answers are grounded in the most up-to-date and relevant information. Updating external data. Since external data can become outdated, it must be periodically updated. So in this case, you can keep every time, every second, you can update your database, or you can schedule some term, some period every that cycle that your database can be updated. So new documents and datasets are ingested and their embeddings are refreshed in the vector database. Updates can be handled in real time or through scheduled batch I mentioned before to keep the retriever system accurate. So this is another flowchart of RAG. So this is user query. And when it goes here, then it goes to embedding store. And this is our source data. It became chunk and converted in embeddings to stored in embedding store or vector DB. When the queries become embedding vector and goes to the store and it retrieves the information, combine the retrieved information and user query here, and it sends to the LLM to make the response. And it makes the output and we see that output. So now I'm gonna talk about the prompt engineering, RAG, and fine tuning. Those three are continuously compared in technique of AI. And the first prompt engineering is the critical process in artificial intelligence that involves structuring instruction or prompts to guide generative AI models to produce coherent, relevant, and high-quality responses. With the rapid advancement in AI, the role of prompt engineering has gained prominence, bridging the gap between AI models and end users. The prompt engineers can craft and optimize input that ensure AI applications deliver accurate and contextually appropriate result. So prompt engineering is the part of making the prompt which will be sent to AI or LLM models. And as I mentioned before, better prompt generates better responses. The benefit of prompt engineering is it improves the AI efficiency. By constructing prompts that guide the AI model precisely, prompt engineering enhances the relevance and coherence of responses. Also, proper prompt strategies can maintain consistent and higher performance. Moreover, it can reduce redundant API calls and token usage, meaning less cost. Also, the versatility. versatility. The principles of prompt engineering can be applied across various AI domains, including natural language processing, text-to-image models, and conversational agents. Also, I'm gonna talk more about later, but I guess that prompt engineering is very versatile that we can implement in everywhere where it gets the prompt as an input for their output. The key components of prompt engineering, sorry for the typo, is the first one is instruction or task. The clear and specific instructions outline the desired action or response. Also, it has questions which guide the AI to focus on specific area and provide concise information. The context is also important. So adding context ensures the response aligns with specific scenarios or user needs. It will become like information or background that helps the model generate responses relevant to the specific situation. Also, it can have input data, which the input or question that requires the models to respond. Output indicator specifies the type, format, or structure of the desired output. It's something like if I need some in chart, then they also can give a chart like this. Also, it can have some role, which assigning a role helps contextualize the response to a specific person or function. So in here, it does our prompt doesn't have every things in here, but it's important that they have some part which is fit to their information or the prompt. Then we can increase the efficiency and the quality of the output from the LLM. And it also have the limitation. First one is the dependence of model understanding. So prompt performance is limited by the underlying AI model's capacity to interpret and execute complex instructions accurately. Also, we can have trial and error. Crafting effective prompts often requires extensive experimentation to refine phrasing and structure. Also, it has some risk of bias. Poorly designed prompts can inadvertently introduce bias, leading to skewed or inappropriate outputs. So I'm gonna now compare the difference between RAG and model fine-tuning. While both RAG and fine-tuning aim to improve the performance of AI models, they differ significantly in their approach and application. So first, I'm gonna explain about the fine-tuning. So fine-tuning involves taking a pre-trained language model and adapting it further using a specialized data set for a specific domain or task. The decision to fine-tune a model depends on the intended application, as different tasks or industries require tailored optimizations. While LLMs demonstrate strong general performance, they often struggle with domain-specific or task-oriented challenges. Like, even though they can get some generally great score in over every subject, but they might struggle on some very specific narrow part when they're answering. But fine-tuning addresses this by improving model accuracy in specialized application while reducing computational cost. By fine-tuning, we can enhance the performance of for particular tasks such as sentiment analysis, question answering, or document summarization, making them more effective and precise in real-world scenarios. So there are four types of fine-tuning approaches. The first one is supervised fine-tuning. This is the most commonly used fine-tuning method where the model is trained further on labeled dataset for a specific task. For example, in sentiment analysis, the model is trained with text samples labeled as positive, negative, or neutral to refine its ability to classify emotions. So we do train again with the pre-trained model, but first model can be unsupervised, but the second, when we do fine-tuning, you're trained with the data which is labeled. So we are doing supervised learning again. Second one is few-shot learning. When acquiring large layered dataset is difficult, few-shot learning helps by providing the model with a small number of example texts within the input prompt. This technique enhances texture understanding without requiring extensive retraining. So also we have transfer learning here. While our fine-tuning is a form of transfer learning, this approach specifically adapts a model for a task different from its original training objective. The model retrains knowledge from a broad dataset and applies it to a more specialized or related task. Last one is domain-specific fine-tuning. This method adapts the model to particular industry or field by training it on domain-specific text. For example, for fine-tuning model on medical records allow it to generate and understand text relevant to healthcare applications. So I'm gonna explain about the difference between RAG and fine-tuning. So RAG involves augmenting an LLM with access to a curated and dynamic external database. So it retrieves relevant information in real time to generate responses and enhances the model's data accessed by integrating external knowledge. But fine-tuning involves adjusting the internal parameters of the model by training it on a specific label dataset, improves the model's performance or for particular tasks or domains, and modifies the model itself rather than expanding its access to external data. So here says, can we say like RAG is better than a fine tuning? And I can say that RAG is generally better for most enterprise use cases. This is because it is more secure, scalable, and cost efficient because it limits the cost by leveraging existing data and no need for training stages. So when we do fine tuning, we're training twice or maybe more. And here we need more data, which needs to be labeled. And there's like Fishhat, we have some strategies with doing less data set, but still we have to do it. Or so it doesn't have to worry about the data to be outdated because RAG is can be kept refreshing their database. It is also better for security and data privacy, reduce the computation cost, and provides relevant and trustful responses by getting information from the latest data set. So now I'm going to also compare with prompt engineering. So choosing between prompt engineering, RAG, and fine-tuning depends on specific needs and constraints. Prompt engineering offers a cost-effective and flexible approach for enhancing model performance through refined prompts. RAG provides dynamic and contextually rich responses by integrating retrieval mechanism with generative models. Fine-tuning delivers high accuracy and task-specific optimization through retraining on targeted datasets. So fine-tuning can have better accuracy because they are training with specific relevant dataset again. But in perspective of the cost and other perspective like privacy, we would say that RAG is better for here and prompt engineering is the most cost effective, but it still needs some experiment for getting better prompt, and it's not that much accurate compared to RAG and fine-tuning. But in here, you're saying that we can say that RAG, here's the perspective for using RAG, that even when we use RAG model, it is important to have the better prompt when they want to get better answers. So from here, we also need prompt engineering. Also, we can also have fine tuning when we are further LLMs in RAG models. So those three can be used independently, or they also can be used at the same time, integrating each other, and we can have better outputs. And lastly, I'm gonna explain about the LangChain. This is the usable frameworks for implementing RAG. So it's licensed, it's MIT licensed, open source, so it's free to use even for your commercial use. So language is Python based, and LangChain allows developers to integrate various tools and APIs to build RG systems effectively, supporting different data sources and enhancing text generation through information retrieval. This is Ant, and thank you for listening my peer teaching. Thank you.